So what we're covering today is 1.3, chapter 1.3. It's not going to take us too long to get through it, mainly because this is nothing new. Again, we're talking about here imaginary numbers. We've talked about imaginary numbers before, and this is really comes into play and is very helpful with solving quadratics or talking about numbers that are really not definable when we hit something like, as we have here, the square root of -1, where we're trying to get these values. A lot of places that this does come up is in electronics or electrical engineering. It comes up a lot because we need a way to talk about circuits and the flow of electricity and the flow of current for the entire system. We can't have it set up for just when it's working. We need it also to understand and have the equations work when it's not. We need to be able to define the entire function when it's on and when it's off, not just one or the other. And a lot of times, especially when the current is not flowing, we consider it to be kind of dealing in these complex numbers because it has the potential for energy. It has the potential for work, but it's not actually there. So it's kind of one way that we can define it is with these imaginary numbers because it is there and we can conceive of it, but it's not actually working. So that's one place these come in. Now, we went through this before, so I is the square root of -1, and I squared is equal to -1. So I is the square root of -1, I squared is equal to -1. And especially if you continue on with a lot of, or some, not all, because I doesn't come up into every course of mathematics you will take, especially going up, or as I have kind of come to call them, go down, because there are classes above calculus and going up from there. But most of those are you're looking more at the floor or kind of the structure that holds it up. So I think it's you go down to the basement and see how it works. But in some of the engineering classes these come up, and I feel that obviously remembering that I is the square root of -1 is essential, but it is also helpful to remember that I squared is -1. So a lot of times when I'm working through problems or going through them, if I see this I squared come up, I just go on and switch it with -1. Instead of waiting till the very end and we get bigger powers of I, it's easier to just switch it out. -1 multiply, it's just changing the signs. So we have these here. If b is a positive real number, then the square root of -b is I squared of b. And when we work through these, we'll have to be switching this here. We can't just multiply them together with the negative. We have to apply this first and then go from there. So if we were going to say rewrite each one of these here, one of the calculators that I think y'all are learning is, for those of you who had me for trig, is very useful is the TI-30XS. I have a feeling by the end of the class you used it more than you did the graphing calculator, because there's a lot of stuff that this can do, and it's a lot easier to type things in. So we could go second square root -25, and it gives us a domain error. Because unfortunately, it cannot think with imaginary numbers. It just doesn't work that way. The graphing calculator. Now here, we have to go into mode. And you see about halfway down where it says real A plus BI, and the next one is RE to the theta I, polar form. We want it in A plus BI. A plus BI form is complex form. So it can think and do stuff in the complex plane. And so what we can do here is say second square root -25, hit enter, and it tells us that it's 5i. Now this works nicely because 25 is a perfect square, and it can figure it out nicely. Unfortunately, if we said second square root -26, is 26 a perfect square? No. So if we were just saying taking the square root of 26 for the 30XS, it would just say it's the square root of 26. There is no perfect square. That's as simplified as it gets. And leave it there. Here, it's going to convert it to the decimal. The graphing calculator will always go to decimal form. Now there is ways to get at what the square root of 26, which is just going to be 26, through the calculator, but it involves, I have delved a little bit into it, not far enough to really comprehend it, but it involves a lot of graphing and a lot of approximations to finally get there. It's more work than it's worth, especially when I can come over here, clear this out, say second square root 26, it's the square root of 26, and we can move on. So for us here, kind of off that sidetrack, we saw that this is 5i. Now the main way we can think of these and go through these is, well, if I see a negative inside an even root, square root, it's going to come out as I, because the square root of -1 is I. So for this one here, we can take that negative out as I. Because what we're saying, is really that we're saying that the square root of -1 times the square root of 12. Well, the square root of -1 is I. Now we need to see what the square root of 12 is. Here, we can go, clear that out. Second square root 12 is 2 square root of 3. But we weren't just looking at square root of 12, we were looking at square root of -12. So it's going to be 2i square root of 3. Questions on this here? We can do the same thing with the square root of -13. Well, we know the negative is going to come out as I. Then we need to take the square root of 13. Is 13 a prime number? Yeah. So it's going to end up being just I square root of 13. Questions on this here? We got to remember this as it's coming back to us. Multiply or divide as indicated. When we multiply or divide, we really need to simplify the radicals first and then multiply them together. Because it's very tempting to want to just smash them together and go from there. But 9i, square root of -9. Well, the negative is going to come out as I, yes? And what's the square root of 9? 3. So the square root of -9 is 3i. And we're multiplying it with the square root of -25. Well, the negative is going to come out as I. Square root of 25 is 5. Now we can multiply those together. 3 times 5 is I times I is I. And we know I squared is what? -1. So really that's saying that we have 15 times -1, or just -15. It is very tempting to want to multiply those together to say the square root of -9 times -25. But it gives us the correct number but wrong sign. Because the properties with negative inside radicals gets a little tricky in that part. Simplify each one, then multiply what we get. Does that make sense? Well, if you noticed, the one above, -9 times negative, it does work. The calculator does get it, but if we put it together, it doesn't give us the correct sign. It still works, it works properly, but the properties of negatives inside radicals are tricky. Because if they weren't negative, it was just square root of 9 times square root of 25, we could just slam the two together, 9 times 25, solve it from there. The negatives is what makes this work weird. Questions on this here? So we'll go on and do B, because here we can take I out and we have the square root of 15. Second square root 15 is square root of 15. I squared of 15 times. We take the I out and square root of negative 3. We get I squared of 3. Now we're going to multiply them together. I times I is I squared. 3 times 15 is 35. Will the square root of 45 reduce? What are the two factors of 15? Because we have 1 and 15 or what? 3 and 5, yes? What did we just multiply 15 by? 3, yes? Do I now have 2 3s? So it will reduce. And we could also plug it in and see it's 3 squared of 5. So we do have 3 squared of 5, yes? We also have I squared. What is I squared? Negative 1, yes? So if we're multiplying something by negative 1, the value of the number doesn't change, only the sign. So it's just really saying negative 3 square root of 5. Questions on this here? Here, we can simplify the numerator and denominator. So the numerator, well, we're going to have I, yes? We can take second, square root 50, which is 5 square root of 2. Denominator. We get I squared of 2. Anything divided by itself is 1. So this reduces to 5. Questions on this here? Not too bad. Now, in Algebra 2, I really switched back and forth. I mainly just called everything the complex number, because according to the fundamental theorem of algebra, any solution or any number can be rewritten as a complex number. So we'll have a real part, which is our term without I, and we'll have an imaginary part, which is our term with I. And I don't know if they were being funny or joking around, but if you force your real part and your imaginary part all at the same time, try to coexist, it gets a little complex. Complex numbers. I don't know. Maybe that's just a joke I made up. But we call this a complex number because when we take the real and imaginary part and put them together, they're considered a complex number. Now, any number can be rewritten as a complex number, even if we just had the number 7. Because I can say 7 plus 0i. That's a complex number. Even if we had, say, negative 7i, well, I can still rewrite it as a complex number with a real and an imaginary part. It just means one of them is going to be 0. Still a complex number. Simplify each expression and write the result in the form of a plus bi. So really, for the most part, it's just simplifying these radicals and seeing what we get. So for the first one, 3 is fine as it is, minus square root of a negative 100. Well, the negative is going to come out as I, leaving us with the square root of 100, and the square root of 100 is 10. Three minus second square root 100, well, times negative 100. 3 minus 10i. I did the times negative 1 because I forgot to put the negative in front of the 100. 3 minus 10I. So on some of them, it does work out well. Now, we can move on to the second one, 2 plus 7I over 5. On a whole, these aren't that bad because they've already kind of done everything for us. We don't have to simplify the denominator. All they're asking us is to split it apart. Because if we take two fractions and add them together, if the denominators are the same, we add the numerators, yes? Almost doing the same thing in reverse. So if we split them apart into two fractions, the denominators have to be the same, because the only way we can add them together is if the denominators are the same. So if we split it, the denominators are still going to be the same. The sign that goes between them is whatever sign's on top. Since we're adding them together, we're going to add the two fractions. On top of the first one's 2, second one's 7, and we have I. So in this case, A is 2/5, B is 7/5, and that's it. The first one, A was 3 and B is negative 10. Questions on this here? Now, the denominators won't always be the same. They don't have to be the same, but they are the same when we split it apart. So the next one here. So we can split it apart first into our two fractions. Since the negative 6 and the square root of negative 18 are being added together, our sign's still going to be plus. The denominators are going to be 9 and 9. Yes? Nothing groundbreaking so far, right? Now the numerators, one of them is going to be negative 6. In the other one, we can write the square root of negative 18. I'm of the mind, and especially at this point, y'all have a good concept of simplifying and working this out as we go, yes? So we could rewrite square root of negative 18 there. Let's just simplify it, because we're going to have to simplify this anyways, yes? The negative is going to come out as I. Square root of 18. Second square root 18 is 3 square root of 2. So we have 3I square root of 2. Now we do need to simplify. Because 6/9, negative 6/9 is going to become negative 2/3, because they both have a common factor of 3. That will simplify out. Plus 3/9 reduces to 1/3, yes? Now we don't have to write the 1 in the numerator if there's something still left there. The I we can move over to the side, and the only thing we have left up there is square root of 2. So that there is your final answer. Questions on this here? Feel pretty comfortable with that there? Now, as I said, so we still got both denominators 3. That's fine. That works. It's not always has to be that way, because if, say, the other it was 4I instead of 3I, 4 and 9 don't reduce. So then we just ended up with 4 square root of 2I over 9, and the other still in thirds. So having those not be the same is nothing crucial. It's just one reduced further than the other. And that can happen. Questions on these here? Powers of I. In Algebra 2, we went through the entire process, and probably some of y'all remember it more closely than others, because we started out with I, setting I equal to the square root of negative 1. And then we squared it, then we cubed it, then we took it to the 4th power, 5th power, 6th power. We kept going till y'all saw the pattern of how this worked. And the power ended up being that we have I, negative 1, negative I, and 1. Because for any power of I, it reduced to one of these 4, no matter what we did. And there's many different ways, well, not many, there's several different ways to go about doing this, because we can group it, depending on the power, we can do groups of 4, and then see what's left over, and that'll help us figure it out, or other methods. And the best method I found for I to the nth power, whatever n is just the exponent. We take that exponent and divide it by 4. Take that exponent and divide it by 4. And we're going to get 1 of 2, 3 things. Because quarters, fourths, we get 0.00, 0.25, 0.7, or 0.5, and then 0.75. 4 values that we get. If you get 0.25 as the decimal, it's going to be I. If you get 0.5, because I normally put 0.50, 0.5 is the same thing because the calculator normally drops the excess zeros off. We get 0.5. We get -1. If we get a decimal 0.75, it's -I. And if you get 0.00, it's 1. Or really, if it's 0.00, it's a whole number. We don't have a decimal, then it's going to be 1. So really, for any power, we divide it by 4, and we get the answer. So even looking at these here, so I to the 48th. Well, I can grab a calculator and say 48 divided by 4 is 12. I don't really care or have too big of a focus on 12. I'm looking at the decimal. And the decimal is 00. All the 12 is telling us is that we have 12 groups or 12 multiplications of I to the 4th. So I to the 4th multiplied by itself 12 times is what we have. All we care about is that this is 1. And we do the same thing with 23rd. I to the 23rd divided by 4, and we get 0.75. So that tells us this is -I. Then we can do the same thing with 50 and -19. They're going to work a similar way. Now we can plug them in the calculator. I to the 50th. And we get -1. Then we can do I to the -19. It's going to throw it for a loop. Yep. It is -1. -4.75, so we get I. This is the first time I've seen them actually use negative powers for these here, so it's a little bit different. Well, wrong calculator. 0.75 I. Yep, because 0.75 is supposed to be -I, yes? Yeah. Because the reason this works a little funky, we need I to be to a positive power. Properties of exponents. To make the exponent positive, we move it from the denominator to the numerator, numerator to the denominator. We flip from one side to the other. I to the 19th. Well, we already saw 19 divided by 4 is number 0.75, yes? So that's saying that we have 1 over -I. We can't have I in the bottom of a fraction. Because really what we're saying is that I have 1 over the negative square root of -1. Having a negative, or just not even negative, just having a radical in the bottom of a fraction is not good. So what we're going to do is multiply top and bottom by the complex conjugate. Complex conjugate is we take the sign in front of I term and flip it. So if it was 2 plus 5i, its complex conjugate is 2 minus 5i. And multiply these together. 1 times I is I. -I times I is -I squared. Which is really saying I have I over -1. I'm just being I. Does that make sense? It's a funky way to do it. It's really weird. But the graphing calculator can do these, because if you looked at the first I to the negative 19, it does give us the answer. That e to the negative 19 is an approximation error. What it's doing to calculate these is graphing I, technically graphing the function and then approximating this according spot. Once it gets so far or so big in certain places, and again, it's using the graph. The graph has pixels. So that number it's getting here, that negative 1e to the negative 13 is a pixel size. It's massively tiny. So if you plug them in, whichever one has that e to the negative 13, negative 12, that big number, consider it 0, even if it has I. So that's 0, so really the only thing we have is positive I. That's the answer. Does that make sense? Because for some, we can say second I to the negative 20, it works out just fine. Some it has issues with. Any other questions on this here, or any questions on this here? I think we're getting close to the end of this. You know where our pages are at. Got multiplication and then division, so we're almost there. Whenever we add or subtract any complex numbers, we add the real parts, add or subtract the real parts, add or subtract the complex. So if we look at the first one here, so negative 2, we get from this here, minus 4i. I'm going to rewrite it without the parentheses. We can drop them with the first one because it's positive. The second we can do the same because it's plus 5, plus 2i. Because we have plus in front of the parentheses, we're just multiplying the whole thing by positive 1, which is going to change nothing. Now the next one, we multiply it by negative 3, or not negative 3. We multiply everything inside here by the negative. So we'd have negative 3 minus 6i. Because the minus ones are the ones we need to be careful of just so we have the correct sign. Now what we're saying is we have negative 2 plus 5 minus 3. What is negative 2 plus 5? 3, yes? Minus 3 is 0, okay. Those 3 are gone. Negative 4 plus 2i. Negative 4i plus 2i is negative 2. Minus 6i is, so your answer is negative 8i. Yep. Graphing calculator. Negative 2 minus 4i plus 5 plus 2i minus 3 minus 6i. And I think yep, I see what I did. Okay, now I'm going to fix my error here in a second. I'm going to explain this first. So that's the answer. The graphing calculator can do addition, subtraction, any of these here, as long as we don't have a radical that doesn't reduce. So instead of saying the last one was minus 6i, it said minus the square root of 6i, the calculator is going to throw a fit. It's going to want to approximate it to decimals. Does that make sense? Let me pull it up here. It said this, or the square root of 6 instead of the 6. The graphing calculator wants to keep it all decimals, try to put everything together. It doesn't like reducing radicals. Now, my error here. What's a negative times a negative? I love it. Because I was talking a good bit, putting a big emphasis on making sure that we got the correct signs, and I got the wrong sign. So it's very easy to do. It's something that's definitely be paying attention to. So, and that's also why I do put a big emphasis on it, because it is so easy to do. But that's it. With these here, we can do that. Even with fractions, the graphing calculator can do it for us. As long as it's not a radical, it'll work just fine. So we good with addition and subtraction of these here. I think, yeah, I'm just making sure, example 6. Okay. Multiplication. We're just multiplying them together. The graphing calculator can do it, but any one of these here, even with the square, we'll look at it. All we're saying is that we're multiplying this by itself. 3 plus 4i squared is multiplying it by itself. So we multiply through, we can do it part by part. 3 times 3 is going to be 9. 3 times 4i is going to be plus 12i. 4 times 3i is going to be plus 12i. And lastly, 4i times 4i is going to be plus 16i squared. And at this point here, we'd simplify. Well, we do have that these are like terms. And what do we know about the I squared? It is -1. And again, when we went through this in Algebra 2, a lot of times when we're going through the first time, we would rewrite this back out as 16 times -1. But we know 16 times -1, it's still going to be 16. It's just that this is not going to be plus anymore. It's going to be minus. And a lot of times when I work these, we understand the times the -1. I will cross that I squared out, change the sign from positive to negative or negative to positive to take that into account. So we do 9 minus 16 is -7 plus because I am all for, if we can do it simpler, let's do it simpler. If we don't have to rewrite this out just because we're wanting to rewrite I squared as -1, I'm all for it. If it is helpful for you to rewrite it back out, rewrite it back out. Does that make sense? Do what's best for you. Don't do it just because I'm doing it this way. 3 plus 4i squared. The graphing calculator can do it just fine. Oh, this is literally the last thing. Good. Now with multiplying or dividing complex numbers, we have to use the complex conjugate. I delved into a little bit when we had I to the -19. So doing this first one here, a, if we're to simplify it, we multiply it by the denominator's complex conjugate. So 3 minus 5i, we'll still have the 3, and we'll still have the 5i on top and bottom. But instead of minus, it's going to be plus. And we can multiply it out. So the numerator, we're going to 8 times 3, which is 24. 8 times 5i is going to be plus 40i. Then we do 2 times 3i is going to be plus 6i. And lastly, 2 times 5i is going to be plus 10i squared. Now the denominator, we can multiply it all the way out. 3 times 3 is 9. 3 times 5i is going to be plus 15i. Negative 5i times 3 is going to be negative 15i. And negative 5i times 5i is going to be negative 5i squared. 25i squared, sorry. 5 times 5 is 25, not 5. Now in the denominator, the 15i and negative 15i will cancel each other out. That's 0. Well, we know that the I squared is going to turn this negative 25 2 plus 25, because negative 25 times negative 1 is positive 25. And 9 plus 25 is 34. The numerator, 10i squared, we're going to change it to negative 10. So we can say 24 minus 10 is 14. 40 plus 6i is going to be plus 46i. Now at this point here for Algebra 2, when doing it by hand, I accepted this as the final answer. The math program that we have and what it's asking for is going to throw it out because it wants it in a plus bi form. We have to split this. So we'll have 14 34ths plus 46 34ths I. Now 2 will go into both 14 and 34, which will give us 7 17ths, which is simplified as it gets. 1 because 7 doesn't go into 17 and 7's prime. So plus 2 will go into both of those for sure. So 2 out of 46 is 23, 17. I didn't get back to example 6, but that's fine. Same exact thing. Now the graphing calculators that y'all use for Algebra 2, you have to do a whole different method, but these here, the ones that I gave y'all to use in class, we'll do it. Let's look at even the next one. Well, it's very tempting to want to type the next one in the calculators, but what do we have? Square root of negative, or square root of 3, yes? The graphing calculator is going to throw a fit. Well, not throw a fit, it's just going to put it into decimal form. Now with the negative 1, all that's telling us is that we have 1 over 2 plus square root of 3i. 2 plus square root of 3i. So that just means that we're multiplying by the complex conjugate. Now with this here, the numerator is very nice because we're multiplying it by 1. So we're just saying 1 times 2 minus 3i, square root of 3i. It's going to be 2 minus square root of 3i. That's nice, that's easy, it's good to work with. The denominator, we can multiply it out. 2 times 2 is 4, minus 2 square root of 3i, plus 2 square root of 3i, minus, because I think we're good all the way up to that point, yes? Square root of 3i times negative square root of 3i, positive times a negative is a negative. Square root of 3 times square root of 3 is 3. We could say the square root of 9, which is going to reduce to 3, or the square root of 3 squared, which is still just 3. And I times I is I squared. There is no simplifying with the numerator because it's just 2 minus square root of 3i. There's nothing else. There's no like terms. There's no i's to powers. So it's as simplified as it gets. The denominator, negative 2 square root of 3i and 2 square root of 3i make 0. The I squared turns that into a plus. So we have 4 plus 3, which is 7. Which tells us that we have 2 sevenths minus the square root of 3 sevenths I. questions on this here? Good with this here? Now the last one, really we would multiply by the complex conjugate. So that would be negative 5i on top and bottom. Yes? Are there any radicals? Alpha y equals, enter, negative 2 over 5i. Negative 2/5 I. And a would be 0. And that's it. The only other part I realized I skipped over was example 6. This is just multiplying. Same thing as what we did, just in a little bit simpler terms. So that's the end of 1.3. Go on and do that assignment and get